Okay, so I forgot to record this in class, so I'm recording this after school. Positive I'm going too fast. I have no idea if my pacing is good without students here. This is the warm-up. I recommend you do 2 and 3 first. On 2 and 3, you're trying to find the perfect A and B to make this handoff of a cube into a parabola both smooth, so it's continuous, and differentiable, so there's no sharp turns. You should treat both of those with limits. So for continuity, you would say the limit as x approaches 1 from the left, which would use ax cubed plus b, needs to equal the limit as x approaches 1 from the right, which would use x squared. If you evaluate each limit at 1, you get a plus b needs to equal 1, and that's one thing that needs to be satisfied for them to meet. The other thing that needs to be satisfied is differentiability, which is to say that slopes need to smoothly match each other so there's no sharp turn. That implies that the limit as x approaches 1 from the left of the derivative, 3ax squared, no b, equals the limit as x approaches 1 from the right of the derivative, 2x. From that, you get that 3a needs to equal 2. That gets you a. Then you can find b. That's the idea. Now, a harder type is number 4. Try number 4. It's where you're proving the derivative doesn't exist. And it's a little harder. You have to use the definition of the derivative. It's not quite like these, where you're just doing the limits of the derivative. You're using the definition of the derivative itself. I changed it so it is continuous. So my first option would be to say, oh, it's not even continuous, so that's the easiest way to prove not differentiable. You can see, if you get a quick look, that 1, the left branch is 3, and at 1, the right branch is 3, so they do meet at 3. It's not a question of when they meet. It must be the case that the slopes don't match. So you are supposed to show that f prime at 2 does not exist, which means show that the limit as x goes to 2 of f of x minus f of 2 over x minus 2 does not exist. That's the alternate definition of the derivative. If the derivative doesn't exist, it must be because the definition of the derivative is breaking down. Using one-sided limits, the limit as x approaches 2 from the left for f of x would use negative x plus 4 minus f at 2. F at 2 is the upper rule. When x, not 2, should be 1, shouldn't it? Sorry. You probably wonder what the heck I'm talking about with 2. It says x approaches 1, not 2. As x approaches 1 and f at 1. F at 1 uses the upper rule. At 1, the upper rule comes out to be a y value or an f value of 3 over x minus 1. All right. In other words, I used the definition and I applied negative x plus 4 for f of x because that is the part of the function that applies for x less than 1. If I evaluate that, I need to clean it up. I get something like negative x minus 3 over x minus negative x minus plus 4 minus 3, which is negative x minus 1 plus 1 over x minus 1. With factoring out a negative and then canceling out, you'd see that that is negative 1. Now that actually makes a lot of sense if you think about it. That left-hand shaped graph is a line with slope of negative 1, so that the derivative being negative 1 is totally logical. If you then do the left hand or the right hand limit of the slopes, the right hand limit when x is greater than 1 uses 2 plus x squared for the function minus f at 1 is still 3. That's the limit as x approaches 1 from the right. That's x squared minus 1 over x minus 1. You've done that a lot. You know that if you factor and cancel an x minus 1, you'll be left with x plus 1. If you evaluate x plus 1 at 1, you get a slope on the right-hand side of 2. That means then that you've got a slope of -1, then quickly changing to a slope of +2. Because -1 is not equal to 2, f prime at 2, or the derivative definition itself does not exist. That's the idea. All right. And then the last warm-up is meant to lead into today's lesson. Back in set 76, you did odd powers of trig, integrating odd powers of trig. The idea is you want to set up a u sub, so you focus on the term with an odd power, and you strip it off so that you have sine squared, and the other little sign that's left, you push off to the side, and you'll find that this will later become your du in a u sub problem. Hopefully you've been seeing that and you've been correcting your mistakes, so this is pretty solid by now. All right, now if this is all going to be du, then u needs to be cosine. So my next objective is to change that sine squared to 1 minus cosine squared by identity. That helps me in one step. When I distribute, I get something like cosine squared minus cosine to the 4th sine. Now it's all set up to be a u sub. If you let u equal cosine, then du is negative sine. Be careful there. So negative du is actually sine of x, which is what we have to substitute. Problem then substituted in becomes u squared minus u to the 4th times negative du. From there, you can distribute the negative, integrate, and sub back in your home free. All right. If you're not sure on how to finish that, let me know, but you should be good from there. Now let's take that then and take it into today's notes. These notes are on the back of set 76's notes. They really go together. Set 76 was integrating odd powers of trig. This is integrating even powers of trig. So get out your notes from set 76, which are blue or green. I can't remember which. I think they're blue. Turn to the back and you'll find these notes, all right? Now, back in pre-calculus, you learned the double angle identity for cosine. It was cosine squared minus sine squared is equal to cosine of 2x. I'm sure you learned how to develop it. It comes from the double angle identity, but we don't need to go there. Now, we usually, we had other two equivalent forms. If we wanted to do a form of this that was cosine only, then I could take the cosine squared or the sine squared and replace it with 1 minus cosine squared, and that would make everything in terms of cosine. And I could eventually distribute and combine like terms and get something like 2 cosine squared of x minus 1 is cosine of 2x. Likewise, I could take that identity and replace the cosine squared with 1 minus sine squared, so that the left-hand side was all sine type material. That would give me 1 minus 2 sine squared is cosine of 2x. All right. Now in pre-calculus, you usually use these for half-angle identities. That's what these notes are getting towards. We use those for half angles. What I mean by this helpful versus not helpful, it's not important. For now, just understand that we use those to help us find sine of 15 degrees because there's this 1 to 2 relationship. I could make one angle 30 degrees and the other one could be 15 degrees, and I could find sine of 15 or 22.5. I don't really care about sine of 15 degrees in calculus. I care about something else. We use these identities for an entirely different purpose here. The idea is look at the powers here. Sine squared and cosine to the first. We use these in calculus for power reduction identity purposes. It makes it easier to integrate. Some cases. I'll explain in 1 minute. But for now, what you really need to get down and commit to memory is if you took this and solved it for 1 minus sine squared, I could move the 1, move the negative 2, and I would get something like sine squared is 1/2 minus 1/2 cosine of 2u. Don't worry about the x versus u. I just want you to understand it doesn't have to be a single x. It could be 2x. It could be e to the x. It could be a lot of things. It could be a function. U is a function. All right. Likewise, if I wanted cosine squared, if you look here and isolated that, I could move the 1, move the 2, and I would get that cosine squared is 1/2 plus 1/2 cosine of 2u. Those are what we're going to use to do the following problem. If you get an integral like sine squared, the first temptation is to say, oh, just slap a power rule at it, like sine cubed over 3. That, of course, is a logical thing to try because it's power rule, but you can see it does not check. If you were to check that, it would be 1/3 of 3 sine squared, but then you'd pick up a cosine by virtue of the chain rule, and it just goes nowhere. So that is not it. Instead, you have to go a totally different way. So that's where the identity comes in, power reduction. If you take the identity for sine squared and replace sine squared with 1/2 minus 1/2 cosine of 2x, then that square is not a problem anymore. And it's just more like integrating cosine, which we've done before. I'm going to do some cleanup steps on this. If I take out a half, then it's 1 minus cosine of 2x being integrated. Eventually, you're going to do this with mental use of, or do this without use of. But for now, or at least once or twice, I recommend you show the use of to see what's going on. If I let u equal the function within the function, then u is 2x, du is 2 dx, and so if I isolated the dx, because that's what I have, dx is 1/2 du. With substitution, then I'd have a half and 1 minus cosine of u times a half du, so that I get a fourth of my antiderivative. The antiderivative is u minus sine of u plus c, and I could then maybe sub back and get something like 1/4 of 2x minus sine of 2x plus c. Right? Try the next one then, and do it with looking as little as you can at the left, trying to just use your identity first for cosine squared. You can see it'll be almost identical to the work you have on the left, so if you need to cheat and look on the left, you can. Give it a go, and then, or pause it and pause the recording and give it a go, and then I'll check your answer in a second. Okay, so here's your answer. You should have had something like 1/4 of 2x plus sine of 2x plus c. It's pretty much the identical problem, just with addition instead of subtraction. All right, let's see what general little wrinkles can look like. Say you had sine squared of 4x. The identity still is going to need to be applied in that you're going to have to take 1/2 and 1 minus cosine of 2u. Now, when I say 2u, I mean double the previous angle. Well, if the previous angle was 4x, then double the previous angle will be, that's right, good job, 8x. If you then were to integrate this, the antiderivative of 1 is u. This time I'm going to try without use of. Now, the idea of integrating cosine of 8x is sine of 8x, but the question is, what about the 8? When you take a derivative, you have an 8 in front. When you take an antiderivative, it's actually an 8 beneath. So it's something like minus cosine, oops, I said I wasn't going to use sub, and then I put a u there. X, the antiderivative of 1 with respect to x is x. The antiderivative of cosine of 8x is sine of 8x over 8 plus c. You could check that if you want. You could take a derivative on that. The derivative of x would be 1. The derivative of sine of 8x over 8 would be cosine of 8x over 8 times 8, which would be right there. So it feels like it checks out, and that is the antiderivative, all right? If you have a great or even power, then things get a little nasty. So here's the idea. I could try the old stripping off a single, but if I stripped off a single cosine, I'd have cosine cubed and cosine, and that doesn't do me any good because I don't have any identities for cosine cubed. So that stripping off method doesn't work for even powers. It works for odd powers, where after you strip off a single sign to the first, you have sine squared. That's an identity. So it's a different approach here. Start by breaking it into two things I do have identities for, cosine squared. I can make that 1 minus sine squared and 1 minus sine squared, and that's logical, but then I'd get sine to the fourth, and I'm right back to where I started, same fourth power problem. So that doesn't do any good. Instead, use this power reduction idea. I'm going to put a half out front, 1 minus cosine of 2x, then another half out front, 1 minus cosine of 2x for each one. If I clean this up, I get 1/4 1 minus 2 cosine of 2x plus cosine squared of 2x. That stinks. Well, that needs to be dealt with. So that's where another identity comes in. If I were to replace that, I could break this into lots of little integrals. I'm not sure if I should or not. Let me see if I need to. 1 minus 2 cosine of 2x. And this is 1/2 plus 1/2. Oh, darn it. Cosine squared is plus, isn't it? Sorry, these should have been plus the whole time. 1/2 plus 1/2 cosine of 4x. Double the previous angle. The previous angle is 2x. Doubling it now is 4x. All right, so then if I combine like terms here and here, I can integrate three things. 3/2, 2 cosine of 2x, and 1/2 cosine of 4x. Are you down? Here we go. Integrating, 1/4 stays. The antiderivative of 3/2 is 3/2 x. The antiderivative of cosine of 2x is sine of 2x. I'll mentally check that. Does that work? The derivative of sine of 2x would be cosine of 2x times 2. That feels like that's good. 1/2. The cosine of 4x's antiderivative would be sine of 4x over 4. So I think this would be 1/8 sine of 4x. And I'll check that mentally with the derivative. The derivative of that would be cosine of 1/8 times cosine of 4x times 4, which is 4 over 8 or 1/2 cosine of 4x. I think that is correct. And so there is my solution. All right, hopefully that's going okay. Last but not least, an application problem. You try this one. This is good. Combination of skill problems. Give it a go and see what you think. Pause the recording now. All right, did you really try it yourself, or are you always waiting for me to do it for you? Here it is. Sine of 2x is a sinusoid, but the period is 2 pi over 2, so pi, it's happening quicker, and so I'm feeling it's a little tighter wave sinusoid. I'm going to take the part in the first quadrant, the 0 to pi over 2 part, and revolve it about the x-axis. When I do that, the reflection looks like this, and all these little slices would get revolved, and I get a three-dimensional figure, kind of a ball or an ornament kind of thing. This is what it looks like. Is that a disc or a washer, I ask you? Right, it is a disc. No hole in the middle. The region is right up against the axis. It's not a washer. So the volume is pi r squared h, and the radius is Seems like it's varying. Here's the radius, and here's the radius, and here's the radius. So it's tied to the function. So the radius is the function. Sine of 2x. You might write that as sine squared of 2x. That's the same thing. The height is the thickness. The height is dx. That's how tall that disk is. We're integrating with respect to x. And so the limits are x. Limits 0 to pi over 2. All right. Now, how do I integrate that? Well, at the end of this lesson, you should know that you integrate that by an identity. Sine squared is the same as 1/2 minus 1/2 cosine of 2x. If I take the half out front, then now it becomes pi over 2. And I'm looking at 1 minus cosine of double the angle. Now, double the angle, it was 2x, so now it's sine of 2 times 2x. It's cosine of 4x. That reduces the power from a square to a first degree and makes integration easier. That's the idea of the day. The antiderivative of 1 is x. The antiderivative of cosine 4x is sine of 4x over 4. From 0 to pi over 2. If I evaluate this limit at pi over 2, it's pi over 2 minus sine of 4 pi over 2 over 4 minus 0 minus sine of 0 over 4. Almost done. We get something like pi squared, oops, rushing ahead of myself, pi over 2 times 0 minus, this is sine of 2 pi, that's 0, everything's 0, so it's really just pi over 2 times pi over 2. So it is pi squared over 4 is the one. Checked out your calculator, and you can see it is true. Pi squared is roughly 9-ish, a little more over 4. So I imagine something 2 1/4, around 3. All right, that is that. The rest of it, we went over the multiple choice on the test we took, but that's not a released exam, so I cannot do that. And instead, that's the end of the lesson. Hope you had a good weekend, and I'll see you Monday.